consider these two graphs of probability density, two PDFs. These two PDFs that both have mean 0. Mean 0. Let's do this and like that. And I need another one here. All right, so one of them, so they got mean 0, so I'll draw this. It's going to look like that, if you will. And then there we go. I think that's good enough to get the idea. All right, so here's two probability density functions. Both of them have a mean 0. And the point I'm trying to get across here, which, if you believe my sketch, is that they have the same mean, but clearly are different distributions, right? Different, how would you describe this? They have a different spread or dispersion. Dispersion, right? Same mean. This second one is a lot wider and it's a little bit fatter. This one's got much more of a narrow, most of the distribution there is narrowly done, right? So in terms of talking about describing a random variable, if you have a random variable x and you compute the mean or you compute the expected value, that does tell you a little bit about the distribution without having to look at the whole distribution. If I say the expected value of my random variable is 0, then we know that distribution should be more or less have an average value of 0, right? But there's clearly a lot more that can be said. Specifically, what about the dispersion of it, right? What about the dispersion, okay? So what I might do to try to approach this then is sort of say, is there a way to quantify how likely it is for me to get a value that's going to be like over here or this far away on these distributions, right? I would argue that in the second distribution here, I am much more likely to get this value in this distribution than I would be to get that value in this distribution. Maybe not, right? And since, again, we're talking about continuous, I would maybe say like a range of values, from here to here or something, right? So let's say, let's try to simplify this a little bit. Let's investigate this with two different discrete distributions. Let's take x. X has the values 1, 2, and 3. Okay. And the probability mass function here, I'll give us, there we go. What is the mean of x here? Expected value of x should be quick exercise. 1 times 0.3 plus 2 times 0.4 plus 3 times 0.3 here. That's equal to 2. Here's another distribution. Let's take a random variable y. Here's its probability mass function f of y. Now y can take on the values 0, 1, 2, 3, and 4 with probabilities 0.2, 0.1, 0.3, 0.3, and 0.1. And what is the mean of y then? What's the expected value of y? So that's 0 times 0.2. Well, that's just 0. And then we're going to have 1 times 0.1, 2 times 0.3, It's 3 times 0.3 plus 4 times 0.1, and I run that through a calculator, and sure enough, we get 2. Okay, clearly different distributions that have the same mean. Okay? Now, is there a way to sort of quantify the spread? All right, let's think about this. Let me take x, for example. The mean is 2. The mean is 2, all right? Is there a way I can maybe define a, think about this. Here's the idea. I want to like, think of a random variable. Okay, think of a new random variable that is a function on x, right? But the random variable is going to take on values that represent the distance you are from the mean of the distribution. So think of a new random variable that measures the distance from the mean. That's the idea. Think of a random variable that measures the distance from the mean. Okay? So what are the possible distances from the mean if the mean is 2? If the mean is 2, then I could be 1 away from the mean, right? I could either be 1 to the left or 1 to the right. 1 to the left or 1 to the right. Okay? So the distance I could be, sort of think of it as like a new random variable, g of x. So g of x equals -1, that's 1 to the left, with probability equal to, what's the probability I'm 1 to the left of the mean? That would be 0.3. G of x would be 1 to the right with probability equal to 0.3, because that would be taking on the value 3. And then g of x would be equal to 0. It'd be 0 away from the mean with probability equal to 0.4, right? Because that would be when I'm at 2. All right. Now, if I'm talking about distance from the mean, I don't really care if I am to the left or the right of it, right? In terms of negatives, okay? So what I'll do then is I'll look at the expected value of the absolute value, maybe, in this case. Absolute value of g of x, if you will. Absolute value of g of x. Or alternatively, if I don't want to deal with negative distances, right? How else could I make these positives? I could just square them, right? So I'll take the absolute value of g of x squared, or the expected value of that, right? So that's going to be -1 squared times 0.3 plus 1 squared times 0.3 plus plus 0 squared times 0.4. So this is 1 times 0.3 plus 1 times 0.3. That is 0.6. Okay? So that is the expected squared distance from the mean. That is the expected squared distance from the mean. We could do the same thing for y here, right? We could do the same thing for y in some sense, right? I could sort of say, what's the expected value of the squared distance from the mean for y? This is going to have more computations, right? So the mean for y is 2. So let's take a look. What's the squared distance? Let's just go each case. How far away is 0 from the mean? 0 minus, it's -2 units away. I'm going to square that. And that probability that it takes on the value 0 is 0.2. How far away is 1 from the mean? That is 1 to the left. 1 to the left, that's a distance of -1. I'm going to square that to make it positive. And the probability that it takes on the value 1 is 0.1. The probability that it is 0 units away from the mean, 0 units away from the mean, 2 minus 2. I'm just going to square this for the sake of seeing a pattern. That probability is 0.3. 1 unit to the right of the mean. When x is 3, that probability is 0.3. And how about 2 units to the right? When x is 4, I'm going to square that. 0.1. Now, you might be thinking, well, you don't really need to square the positive distances. No, but I do need to be consistent. So either I'm squaring all the distances or I'm not squaring any of the distances. And so I am going to square the distances to make sure that I'm actually adding them up and I don't have things that cancel out. And we can run through this computation and we should get 1.6. 1.6. So the average squared distance in terms of the random variable y, 1.6, is greater than the average distance from in the distribution with x of 0.6, which should make sense, right? Y goes from 0 to 4, and there's positive probabilities all across the board there. X only goes from 1 to 3, okay? So the most I could be away in my x distribution here is 1 unit away. I could be as much as 2 units away with y, and so my spread, it is more spread out. That has a higher square distance. This spread, the computation we just did, this idea is called the variance of your random variable. Called the variance of your random variable. And really all it is it's computing an expected value of a new random variable, where that random variable is measuring the squared distances you can take on from the mean. That's all it is. All right? Let's write down the formal definition then of variance. The variance of x is. I'm hoping that idea, that in that illustration that we just did, develops some intuition, because what I've found in the past is just because the notation here starts to get a little dense in general, is people sometimes get lost or confused in the notation, and it's really not that bad of a computation. It's the expected value of x minus mu squared, the distance that your random variable can take on from the mean. We square that quantity to make sure that the distances are positive, because we're talking about a distance, not necessarily just a direction. Oh, and this letter right here, that is the Greek letter sigma, lowercase letter sigma, squared. Sigma squared. Sigma squared is the notation for variance. This is equal to, in the discrete case, we do x minus mu squared times f of x, just like we did above, and we add up all those values as we do in any expected value calculation. Same idea, except in the continuous case, we replace our summation with integration. Integrate x minus mu squared f of x dx, if continuous. All right, there we go. So we take that. That is the squared distance there. Squared distance, sigma squared. What we can do to get back into the appropriate scale, because these are squared distances, and so a lot of times you might be thinking that's exaggerating the spread. We can undo it at the end and take the positive square root of that number, and we get what's called the standard deviation, the positive square root of the variance, which we denote sigma. That's why we use sigma squared for the variance, because sigma is the square root of sigma squared, is called the standard deviation of your random variable. Standard deviation. Standard deviation. Okay? Standard deviation. All right. That looks good. Yeah, looks good. There we go. Variance. Variance. All right. So what's next here? I got lost in my notes here. There's our variance here. Should we just do an example maybe? Let's go ahead and do an example. Let's say we have f of x equals 2 times x minus 1. When x is between 1 and 2, and it is 0 otherwise. Let's find the variance. Let's find sigma squared. Let's find sigma squared. Okay. So one thing you got to notice here in this definition, this original definition of variance, is in order to do this, you have to know what the mean is, right? You have to know what the mean is. So if I want to find the variance here, first I need to find the mean. We need the mean. All right. So let's go ahead and do that. What's the mean here? Mu, or the expected value of x. And the continuous, this is the integral. Here we're going to integrate from 1 to 2. X times 2 times x minus 1 dx. And we'll go ahead and do the integration here. I'm going to bring out the 2, distribute the x there. So that's x squared minus x dx, integrating from 1 to 2. And we'll work through the calculus here real quick. 2 times, what's the antiderivatives? That's going to be an x cubed over 3 minus an x squared over 2. Evaluate your antiderivatives from 1 to 2. I'll spare us some of the arithmetic here. We should get, I've got 5/3 for that. Just put a light box around that because that's a useful part of the problem here. So we should get that. All right. So there's the mean. Okay, so now how do we find the variance? How do we find the variance? So now we can find the variance. So sigma, let's set this up. Sigma squared then is equal to, let's set up the integral. We have the definition there on the screen at the top. So we're going to integrate, still integrate from 1 to 2. It is x minus mu squared times f of x. So now we integrate x minus mu, and mu is 5/3. X minus 5/3 squared times f of x. And what is f of x in this case? F of x here is 2 times x minus 1. There we go. And that is the correct setup, I believe. Yep, that looks good. All right. All right. So let me scroll down. And now we've got to put our calculus hats on and work through the integration. I might bring out the 2 again. Integral from 1 to 2. X minus 5/3 squared. I'm going to FOIL that out. So that's going to be x squared minus 10/3 x. And then that's going to be plus the square of 5/3. So 5/3 squared should be 25/9. Times this times x minus 1 dx. Remember, I brought the 2 out front there. And then I'm going to go ahead and distribute the trinomial into the binomial x minus 1 there. So I get a nice polynomial here. This is going to be a cubic polynomial. 2 times the integral from 1 to 2. X squared times x is going to be x cubed. So I've got x cubed. X cubed. X squared times minus 1 is minus x squared. Negative 10/3 x times x is minus 10/3 x times x will be x squared. Negative 10/3 x minus 1 is plus 10/3. And then we have the 25/9, so plus 25. Hold on. What something I missed something here. Careful. Distributing this. Negative 10/3 plus, so the negatives cancel. Oh, plus 10/3 x. Careful there. Now I got the 25/9. 25/9 over x minus 25/9. Minus 25/9 dx. There we go. And let's combine maybe. Is it worth combining here even? I don't know. It depends how good you are with your calculator. Because the integrals aren't, the antiderivatives aren't that hard, but I'm going to have to plug in 1 and 2. So let's go ahead and do that. What do we have for x cubes? Just the 1x cubed. What do we have for x squared? We have negative x squared. I have negative x squared minus 10/3 x squared. So negative 1 minus 10/3 is negative 13/3. X squared. And then what do we have for x? I have 10/3 and a 25/9. So 10/3 plus 25/9. And as a fraction, that should be 55 over 9x. And then that's just minus 25/9 at the end there. Just gotta be careful. Hopefully we didn't make any arithmetic mistakes or algebra mistakes. Now we're ready for the antiderivatives. 2 times. What do we have here? X to the 4th over 4. Then we're going to have minus, so this is going to be x cubed over 3. So I'm going to have minus 13 over 3, so 13 over 9 x cubed. Then we're going to have plus 55 x squared over 2, so 55 x squared over 18 minus 25 over 9x, and evaluate that from 1 to 2. All right. So now we got to punch in 2 here, and then we got to punch in and subtract 1. So let's go ahead and try to do this. So this is 2 times, what's the evaluation at 2? 2 to the 4th. 16 divided by 4 is 4. Okay, and then I have minus 13/9 times 2 cubed. All right, and then plus 55 over 18 times 2 squared. 55 over 18 times 2 squared, that's a 4. Minus 25/9 times 2. So times 4. Minus 25/9 times 2. Okay, so that is, I've got negative 8/9 when I plug in 2, minus the evaluation at 1. So the 1 here is just a quarter, minus 13/9 plus 55/18. There we go. And minus 25 over 9 is negative 11/12. All right, so double negative here. This is going to become plus. So I've got negative 8/9 plus 11/12. That is 1/36. 2 times the 36th is 2 over 36. That is 1/18. Got it. 1/18. 1/18. That is certainly a little bit messy, okay? I would recommend if you're doing something like this in the online homework, potentially, maybe once you get to this stage here, consider having maybe punching that into an integral calculator of some sorts, just to save you that maybe some of that extra busy work. On a written homework, absolutely want to see the rest of these steps to make sure we can handle this. Okay, but on the online homework, let's not beat ourselves up over that. All right. Now, a little bit tedious, right? And again, don't forget that this question started out with us finding the mean. All right, finding the mean here, okay? So that sort of begs the next question for me, the next idea that I want to talk about then, is this theorem right here that is, in fact, almost certainly more commonly used for computing the variance. It also says that the variance of a random variable is equal to the expectation of the variable squared minus the mean squared, right? Remember that the mean is just the expected value of x, okay? This is more commonly used. This is much more commonly used. Why is it more commonly used? It's more commonly used because the computation is more friendly, all right? The computation is more friendly. If I can find the mean, if I can find the expected value of x, I can almost certainly find the expected value of x squared, okay? That doesn't change the integral that much at all. Where the integral got messy was dealing with foiling this part out, right? Because when you do the definition here, you've got the x minus mu squared component to work with, all right? We don't open with this definition of the variance because it's not as intuitive what it's measuring. But algebraically, this is an equivalent computation. Algebraically, this is an equivalent computation, okay? So if I continue from the last one, from the previous example, all right, let's find the variance of this again. What do we have here? We know that the mean is 5/3. We know that the mean is 5/3. We found that the expected value of x, or we found that the mean is equal to 5/3. Let's find the variance using theorem 4.2. Theorem 4.2. Okay. Theorem 4.2 says then I just need to find, the next thing I need to find is the expected value of x squared. And then we'll do the subtraction. So let's go ahead and do that. Expected value of x squared. Remember our PDF goes from 1 to 2. And it's 2 times x minus 1. So the expected value of x squared then is just x squared times 2 times x minus 1 dx. This integral is a lot quicker to do than this integral we had here. Now, remember, this isn't the variance, but it's a lot quicker of a computation. So let's go ahead and just do this. We'll bring up the 2, integrate from 1 to 2. Then we have x squared times x minus 1, so that's just going to be x cubed minus x squared dx. Look how nice and simple this is. 2 times x to the 4th over 4 minus x cubed over 3, evaluated from 1 to 2. This is going to work out to be 17/6. So sigma squared is equal to, according to the theorem, this value minus the mean squared. So this is equal to 17/6 minus the square of 5/3. 17/6 minus the square of 5/3. 17/6 minus 25/9. And no joke, 1/18. Much more computationally efficient. All right? So you can do it both ways. You can do it in both ways. We can do this in both ways. All right? And in practice, I will probably be using theorem 4.2 for actually computing the variance. But again, I don't want to go without developing the intuition on what this is actually measuring. You're measuring the spread, and it's the average distance from the mean. It's the expected distance that your random variable is from the mean. The expected distance that our random variable is from the mean here, okay? Oh, these are all variances, right? By the way, these are all variances. So if you wanted the standard deviation sigma is going to be the square root of 1/18, which I don't think is a nice number. So we could just, there's your standard deviation. I would leave it just like that.